dot. Dots. Oh, there it goes. Dots. Dot. Chain. Just messing around. So who likes dot chaining? Hey, dot chaining is great, right? So we're just dot chaining along. It's all good. We can do this with like Lodash or underscore, and that dot value like extracts it or whatever. And we have this RxJS style. It's pretty great. And I'm not talking about fluent interface where we like return this for dot chaining and mutate some internal state. No, I'm talking about just normal data types with dot chaining. So if we were to visualize this, we take this like data into each square, which is like a function, and we're just going to like lowercase it, then split it, then trim it, and reverse it, and so on. It's just this like pipeline, right? Do y'all hear this feedback? Is there a little feedback? Feedback. All right, cool. I'll just talk louder. So by contrast, this dot chain thing is the same function, just like kind of rolled out into imperative style. And if you'll notice, every line is not connected. So the only way they can talk to each other is with introduction of state, right? Like variables or mutating state. So if we were to visualize this, you have these little, it's like that little sock looking thing is the state of California. I don't know, it's the best thing I can come up with. So each of these like commands are state, and they're introducing state, and that's how they communicate, or they're mutating state. Likewise, with object-oriented style, it's cut off a little bit, but it should be fine. So you can see down there, it's got this like, we're talking to emailers and like getting and setting its state and mutating our internal state. And that graph, if you visualized it, would look like this. There's a bunch of getters and setters of objects and other state, which just kind of like fragments the state, right? It's still like this global separate thing that you can alter. And guess what is the major contributor of complexity in apps? We're all, React developers, so we should understand that state is no fun. So it's good to minimize this stuff. The second biggest contributor to complexity would be control flow. And if you think back to the object graph, it's really hard to figure out how the data flows through the application. So we want to kind of wrangle control flow there. And then the third biggest contributor is just code volume or size. So guess what's so good at solving those three things? No wonder we love dot chaining. It's like provably simpler. There's no state. The control flow is just dead simple. We're just piping data through this, and it's actually a little bit more terse, so the volume stays down. So what if I told you there was a conspiracy out there where Morpheus is the bad guy? Can you believe that? You should look this up. It's insane. But what if I also told you we could chain all the things? And you heard me correctly. That is Rick Ross wearing a chain of Rick Ross wearing a chain of Rick Ross. Recursion. Bosses all the way down. So here we have mathematics to help us to dot chain everything. And programming isn't math, or so I've been told. And we have try catch and this prickly syntax and loops and assignment and mutation, not to mention all that stuff that isn't just taking input to output and calculating a value, like network and file work, like those side effecting things that don't just compute values. So we'll call those side effects. So this is our list of things that don't really fit into our nice, beautiful little mathematical world. So remember this list. We'll be attacking this later. So programming isn't math, but this is JavaScript, y'all. So see what we can do here. So we have these two functions, f and g, and we can compose them with this dot. Notice the dot. So that is function composition in algebra, and you can define it as a function that takes an x and just calls f of g of x. So we run g on x and f on the result of that. And the only reason I'm showing you that is because I want you to understand that dot chaining is exactly function composition. So down below you have our to uppercase and trim, and up above it does the same thing. So dot chaining is composition. And what that means for us is we can actually use the mathematics to learn about our programs. And category theory is particularly good at this because it's kind of the theory of composition. It's the theory of like morphisms, going through and composing with other morphisms to define structures. And so if you're subscribing to the idea that composition is program creation, then it's like the theory of program construction or creation. It's pretty cool. So one of the intuitions we get from this is if you take two functions and you mash them together, you compose them, you get another function. And that allows us to keep composing, right? It's only one unit. It scales really well. We're not introducing new concepts as we compose. Another thing that's good about this is if you divide and conquer and break down your problems into like little easy testable problems, little functions that you know work, this gives you a principled way to compose it back together. It's like divide and conquer and then reassemble without any new concepts. And finally, if you're composing, you have this chain of events, right? Like everything is just flowing through it. And if you stop that chain of events, if you like just don't keep dot chaining, you just sever the computation. We're not actually using state to talk to each other, so the right part just gets discarded. So that means everything must be connected. It's a constraint. So let's get a little weird with this diagram. Hang with me for a minute and we'll get to code. So we have this function f that takes an a to b and g takes a b to a c, and we can compose them together and we get straight from some type a to some type c. And what I want to talk about today is this one. Scary. So down below you have this f, this like box type thing, right? And all our little variables are in the box or the type f. And it says here in this diagram, if we can do the thing on the top, we can throw it in an f and then still compose down below. So what is this mysterious box thing, this f? We'll find out here in a second. So let's look at some code. So contrived example number one. We have a bunch of different, it doesn't matter what it's doing. Just notice the output is a down there. So you have this trim, it's a method call, then we have parseInt, a function call, a number, operator there, and we've got a qualified class method. We're doing all these different things and all this assignment. How on earth are we going to be able to dot chain this, right? This is kind of weird, not really dot chainable. Well, we can take a hint from that previous slide and throw it in a box. So here we have the same exact function down below, but thrown into a box, our array in this case. And then we're mapping over it, and that turns out to be dot chaining. We're just composing the structure for our data to flow through. So I know probably a few of you are uncomfortable right now. It's because I didn't pass the 10 to parseInt, isn't it? I'm gonna make you a little more uncomfortable. Bam! New number. Inappropriate use of the number constructor, linter. Take that. So no, I'm proving a point, right? You have this, you can use any syntax in here, and this unifies all our different call syntax, which is really nice. You can dot chain it. Another thing to notice is up above, see all those assignments? We're capturing assignment with our maps. That's really cool. But we're capturing it in a way that's the minimal possible state we can have. Like we've got this little closure where each variable is assigned and then discarded and passed right into the next map. So that's really cool. We've captured assignment, but we kept our cognitive load down. We're not leaving bits and pieces of state in our wake as we write this function. So that's pretty neat. Yeah, the other thing that's probably making you uncomfortable is the array allocation and all these maps iterations, right? So let's fix that. Let's make our own box. So up above, like this works exactly like array. You can imagine it's an array and it's fine. It just holds one thing, right? And up above, we just take some function f, and then we run f on x and return a box so we can keep doing those maps. It looks recursive, but it's not. It's just boxing it back up so we can keep chaining those maps. And if you notice below, our result is box A. And we didn't really want a box A. Actually, at this point, there's no way to unbox this stuff. So let's introduce one more function called fold, and that will remove it from the box. And it's the exact same thing as map. It just doesn't put it in a box afterwards. So pretty intense, pretty heavy, I know. But it's not going to get any worse than this. Oh, maybe it will. Yeah, it's going to get worse. All right. So we're just going to remove it from the box, and boom, we've done all those things that we wanted, right? Like we've captured those three big things, the state and the control flow and the code volume. Well, maybe the code volume's a little bit bigger here, but not so bad. And what we've kind of done is taken these kind of loose bits of data that communicate through this like ambient state, and we've turned it into this. A nice little structure for it to flow through, right? And it takes a little effort to construct that nice, whatever that is, marble madness thing. But it makes your programs a lot simpler. And we've unified call syntax, we've minimized state, we've captured assignment, and forced control flow, all with a box. Hooray, boxes. So we killed assignment. Let's go down the list and kill the rest of these things that make it not mathematical. So loops. This one's an easy one, right? We're not really that, I mean, we know how to get rid of loops already. The punchline is map, filter, reduce, right? That's like 99.999% of loops, unless you're paranoid about performance and then you're writing for loops. But most of the time you can use these and you'll just get rid of it. There is a case, though, where you can't actually get rid of a loop, and that's when you need an unfold. It's kind of the equivalent of a while loop. So I'm not going to go too much into this. I'm just wanting to show you that it exists. There's a function called unfold, and it takes a base case and returns a pair, and just keeps going until you return null. So unfold exists, boom, loop's done. So that was an easy one. Another easy one, it's callbacks. We'll talk about side effects in a minute, but callbacks, we all know how to get rid of callbacks, right? Promises. So I'm going to use a promise in these slides, but I'm not going to use the A+ promise. I give that an F- in my book, but down below here we have it's the same thing. We have map is just then, but we're going to call chain if we're going to return a nested promise. That's the only difference. A+ just calls then each time for both of these cases. We'll use map and chain. You might have heard flat map is the same name as chain, but there we go. That's the only difference. And with promises, let's go into our second example, contrived example number 2. So we're doing 3 things here. We're reading a file, config.json, then we're replacing the contents, and then we're writing a file out. This is a lot of code for those 3 simple things, right? So we could rewrite it with promises like this. Really nice. It's going to read the file, then map over the contents, then write a new file. That's simple. We have to like futurize or promisify, read file and write file. It kind of comes with the gig, but we're all probably using promises here or there, and you kind of know this stuff. So if we compare these two, I actually cut something out. Up above, we've got the console.log success and error handling. Down below, I don't do any of that. And there's a good reason for that. So if we look back at this, we have to call this fork method down below to get this thing to run. And this is a lot like subscribe or .value at the end of your underscore Lodash chain. Basically what I'm using is a lazy promise. And that gives me a lot of benefits. Well, for starters, it takes 2 handlers down there at fork. One is the error one. The first one is your error handler. So you hear a lot of people complaining about promises not propagating the errors correctly. This makes it hard not to. The other thing is we get to kind of compose, we extend the composition. And what do I mean by that? Let's say we're making like a Twitter app. That's like a better Twitter. Like, forget getting rid of harassment on Twitter. We're going to truncate to 130. Better Twitter. So we're going to go through and make this Twitter app and then return it as a library. And then the caller down there, if I call it with my Twitter name, shameless plug, you can go down here and continue to chain and extend the computation because nobody's called fork yet. So that gives you this ability to keep composing even after you've called the stuff. Normal promises would just start running, right? And then the caller, this is the other really big thing that's really important about lazy promises or lazy structures in general, is that when we call fork, usually that gets called once outside of your application. So essentially your entire application is pure because all it's doing is returning new constructors or computations that will run, and then when you actually call fork, they'll run. So each function is just input to output, where the output is just a lazy promise, not actually running. So laziness for the win. It's basically how functional programmers deal with side effects. We push them to the edges or even outside of our application and give it to the caller. So boom, we're way past halfway on this list. This is great. We only have 2 things left. Let's check it out. So branching and errors. Let's knock them off at the same time. So there's this type either. It's not supposed to make you sad. I don't know if this picture makes you sad. So either is a abstract superclass of these two types, left and right. And it's just like fork, what we saw a minute ago. It's going to take a handler, two handlers, and if we have a left, it calls the first one, and if we get a right, it calls the second one. So we have these two types, and they act like boxes. They hold some value, and we can actually map over it. But here, we don't know if we have a left or a right. So this gives us the ability to branch our code. So some function returns us a left or a right, and then when we fold it, it'll either call the first or the second function given to that. So if we have a right, map is going to just map over it per usual and work just like array, just like box, just like promise. And if we return an extra either, we have to call chain to kind of flatten it. But left ignores everything. So left will just ignore the entire map and chain thing because left is kind of, you want to propagate up an error. It's basically like a pure error. So let's see this in action. So if I have this function getConfig up here, and then down here in contrived example number 3, we get the config. If it's there, we'll parse it, get the port. Otherwise, we'll return 3000. And we could rewrite this with either, just like this, really nice and concise. Everything's dot change, no returns and braces and all that stuff. All you've got is a nice, clean pipeline of functions. And getConfig will return us a left or a right. That's what this either try function does. It's the one and only try catch in our app. And then if it's successful, it parses it. Then it folds down either to the left side, which is the default 3000, or the port. And if we compare these two, the bottom right one, I think, is a much better version. Actually, it's going to make you develop safer applications, which we'll talk about later. It's a bold claim, so we'll come back to that. So contrived example number 4. We've got a bunch of nested null checks. And if we've got an address, we'll get the zip. If we get the zip, we'll get the city. If we get the city, we'll return it. Otherwise, we'll return some errors. And we could write that like this. From nullable returns us a left or a right. It's a little helper. If it's null, it returns a left. Otherwise, it's a right. And then it'll chain through each one of those and then call the left branch down at the bottom, either the error or the result. And if we compare these two things, the bottom right one ends up being this smooth data flow, all those things that we did before. We've captured assignment, we've wrangled control flow, minimized state, all that stuff. But here we've got the effect of actually branching or capturing the idea of or disjunction. Boom, that whole list. That's pretty impressive, right? Everything we thought that wasn't mathematical, we could capture. Pretty sweet. Boxes are awesome. So in your day-to-day work, you might write code like this. I actually stole this straight from our code base. So everything's kind of dot chained and easy to just kind of follow the data through the kind of structure we've built. And here, it might get a little long, and you might be unfamiliar with this style, and it might feel kind of gross at first, right? You're like, what is this giant blob of text? But then you realize everything is dot chained, everything is connected, and data flows through. It's like reading a book. It's not like reading a choose your own adventure where each page changes out from under you. You can just come back in 2 years and just walk through the functions and where the data is being passed through. I stole that from our code base. So this might feel uncomfortable at first. It's like constraining, right? Everything must be composed. But then you'll soon see the benefits. I encourage you to give it a chance. There's a few things to know up front. This stuff, it's kind of harder to hack, right? It's hard to just throw something in there, because you actually don't have any space to write some hacky line in there, or just put some line in the middle of this composition. You actually have to extend your program with composable piece. It's kind of like rearranging furniture before you put new ones into your house. You really have to think about before you extend your program. So it's harder to hack, but that keeps you away from tech debt. So it feels good later. And the thing I said about safer programs, go back to contrived example number 3. If I'm a caller of getConfig, that used to return me the file contents. And I could just ignore the error. But now it returns me a left or a right. And if I want to get to the file contents, I have to map over it. And then I have to fold down to get it out. So by doing this, I've enforced the caller of getConfig to handle that error, and that makes safer programs. So you're doing this at construction time, not just getting blindsided at runtime. All right, so that was like the bulk of my talk. That's like what I wanted to show you. But let's get crazy. You know, why not? I want to get crazy here. It's React Rally. I thought I'd type back into React by trying to dot chain an entire React app. So some of this stuff is a little advanced and a little gnarly, but I just want to show you what's possible, and it's kind of fun. So let's get right into it. So suppose we have functions that take some value and return some JSX, right? You take a user and it returns this link. You take a string and it returns this H1. Doesn't matter what the value going in is. We can actually model this like components. It takes some type A and returns JSX. So that's our component. And if our component takes an A to JSX, can we compose it on the right side? Not really, actually, because what function takes JSX as an input? Like, I don't even know of one. And you know, it's not going to preserve composition. We need those variables, those A's and B's and C's, to be able to preserve composition. But we can move it on the left side. Magic. It's going to be pretty cool. So let's go ahead and define our component. I just shortened it to fit on the slides. And this takes our G, our function from A to JSX, and then we'll contramap. Instead of f of g of x, it's g of f of x. That actually runs on the left side. And fold will just run the function, the A to JSX function. So if we actually take our heading here and contramap the page name off of it, instead of taking something, you know, it'll take that A, but it'll actually contramap the page name. So if we throw the entire state at it, it will take the page name off of it and then render into now viewing home. Pretty cool, right? We can just throw the whole state at our function and it knows how to pluck it off. And then we have the possibility of a type of composition called concatenation. Concatenation is actually composition with one type. It's closed. So we can compose components together. And we insert this div to make React happy, but it has no semantic meaning. Shout out to Hardy Jones on that one. So here we go. We have two components up here, profile link and heading. And we're going to contramap both the page name of the current user off of the state, and then we'll combine them together with concat, and bam, we throw the whole state at it, and it renders out a nice page for us, each component taking its own piece of the state. Let's get further, let's get deeper. This is going to get weird, y'all. So reducers. There's two opportunities for mapping, right? We have our A and our B, two variables to map over. And let's make this formal by taking that reducer G, and we'll introduce a contramap and a map. And contramap will run on each element beforehand, and map will run on the accumulator afterwards. So if we run this, or if we look at this, it's kind of a dense example. But the idea here is each element gets contramapped. We add the number is to it. And then afterwards, it maps the exclamation point. And then each iteration, it concats. So what we've done is kind of have a before and after hook of each of these iterations through our reducer with contramap and map. Can we combine them? We all know Redux, combine reducers. Yeah, we can. We can concat these two together, which is, again, composition under one type. And I just stole this set visibility filter from the Redux docs, and here's another one that's just going to add a new to-do. Don't worry about that too much. So we'll take the app reducer, concat it with the to-do reducer, contramap some default value onto the action, and then map last updated after it's run the reduction. And when we fold down our reducer, our like combined reducers, we get the default and the last updated at. So this is pretty cool. This allows us to combine and compose and contramap and map reducers. We could actually even flip the concat and contramap, and now it only contramaps over the app reducer, right? Not the to-do one. So you can actually build out these little subsystems of reducers, contramap and map over there, and then get them prepared to handle whatever state you want to throw at it. And finally, this is where it gets the weirdest. Higher order components, component to component. It's just a function that takes a component, returns one. There's no variables to map over, though, so we can't actually map over it, but we can concat them. So this will actually concat two higher order components. And I'm not actually even doing that in this example. I just wanted to show you could do that. I'm just like putting it in and then folding it back out. But this is the recompose reducer example, or the Redux kind of style example. And we're using our to-do app there to run this. Don't worry about this slide. This was just kind of like to show. All right, so here's our completed app. So what we have down here is we've taken our heading, contra-mapped the page name. We've concatenated that with the to-do app. And I actually had to, if you look at the very top there, I had to, recompose returns this React class. So I had to turn it into that A to JSX function. And there's an isomorphism between the actual functional components and the React classes. So I'm taking advantage of that to turn it into a function, then put it in a component. So it composes with everything else. I hope Recompose considers this stuff, because it would just plug right into this world if we do this. So you can map the page name, concat it together, contra map it, and then fold it all down. And if we take a look at our actual application here, we have this thing, and this is all our code on the left. Let me bump up the font. Yeah, bump up the volume. So there we go. It's the same code here, and we can like add it to do and filter it, and bam. So we've actually composed the entire React application with concat and contramap and map. Pretty sweet. Who's excited? So, thank you. Didn't ask for that applause. All right, so to finish up, map is compose, is program construction, but with like superpowers, right? We can contramap, we can map, we can do all sorts of extra stuff. These are kind of light constructs from category theory, and we actually port more of it to get like die map and all sorts of crazy stuff. And if you really believe in this stuff, like I do, and you enjoy it and think it does reduce the complexity of your application, you might want to learn a few more things. We've seen map and chain and concat, the top three, but the bottom three you might want to take a look at: applicative, traversable, and natural transformations. I have a book. I promise I'll write those last 3 chapters, so you know what those are. So you can check this out if you're into this stuff. A few more shout outs. I have a video series on YouTube, Classroom Coding, if you want to learn more. And I'm working with Egghead to make a series of this stuff, all stop motion, so it's going to be fun. And thanks Salesforce for letting me write crazy ass code and not firing me. That's me. And there's the link to the code and the slides and stuff. Thank you.